Thank you all for coming. In the style of a cinema, I'd like to precede my real talk by a short entertainment. I love back-of-envelope calculations, as many physicists do, and I was having dinner with some people from Shell, the oil company, and they said, if you grew the biofuels to power transport on the verge of the road, on the edge of the road, on that strip along the side of the road, how wide would the strip have to be? So this is a very nice little rough calculation to do, and you say, oh, all right, let's just take one lane of vehicles. Let's assume they're going at 60 miles per hour. Let's assume that they do 25 miles per gallon. Let's assume that the biofuel is produced with 1,200 liters of biofuel per hectare per year. That's a fairly standard figure in European climates. And let's assume the vehicles are 80 meters apart. You take the first number, 60 miles per hour, and you divide it by the other three numbers, keeping careful track of units, and you find the verge would need to be 8 kilometers wide to power that one line of vehicles. To mention a little bit more about the climate motivation, there are some people who call themselves skeptics who say, oh, man is tiny and can't possibly influence things. Natural flows of carbon are much bigger than anything humans do. Well, when I look at data, which these skeptics perhaps don't do very much, I tend to think that humanity can actually influence the system. When I look at data like this, this shows the last 1,000 years of carbon dioxide concentrations measured by looking at fossilized air in ice cores in Antarctica and other places. It looks to me as if something did happen, and maybe humanity had something to do with it. And if we zoom in on this graph, I think we can actually date when something happened. I think it was 1769, and I think we can identify which human did something. Perhaps it was James Watt, who in 1769 patented his steam engine, which was much more efficient than engines that had gone before, and it really got the Industrial Revolution going. So in that ice in Antarctica, we can smell the Industrial Revolution itself starting. And the advice from the climate scientists, based on their models, which still have considerable uncertainties in them, the advice is that humanity should reduce global emissions to zero fairly soon, with a rough indicative figure of perhaps 2 tons per year per person of CO2 in 2050, or perhaps 1 ton per year per person, being strongly advised to avoid the risks of significant climate change and to keep the risk of, say, a 4 centigrade warming below 1% or so. Today's emissions are 5 or 6 tons of CO2 equivalent per year per person. The world average is not, however, shared by all countries. We're not all equal. This graph reminds us of this. This visualizes country by country what the emissions are. The rectangle is the emissions of one country. The width of the rectangle is the population, and the height is the per capita emissions. And we often hear China and India are out of control. They're out of control in the sense that in the year 2000, their emissions were below the world average. The per capita emissions were, for India, more than a factor of 2 below the world average. I think the countries that are actually out of control are these ones over here, say European countries emitting twice the world average, and perhaps Australia, America, and Canada with emissions 4 times the world average. So this is the climate motivation, and just to remind you what 1 or 2 tons per year per person looks like on this diagram, the black line shows 1 ton per year per person. Countries that are examples, role models for this are Bangladesh and Congo. And 2 tons per year per person is shown by the green line here. And the United Kingdom government has adopted a target of reducing to that level an 80% reduction compared with 1990 levels by the year 2050. So we have our 3 motivations for getting off fossil fuels, and in response to these motivations, there's plenty of discussion going on about what to do. And some of the discussion involves emotions and loving things and hating things. And my feeling is such a large challenge that has only been met so far by Bangladesh and Congo is a challenge where perhaps we need, in addition to emotions, which play an important role, we need some facts and we need some numbers and we need some honest, constructive discussion of the facts and the numbers. And that was my goal when I wrote the book, to try and write a factual book that would garner cross-party support from the nuclear, the oil, and the green movements, and from all political parties. And so far, it seems to have managed to do that. My approach is to offer a rough guide to sustainable energy, where all the calculations and numbers are done as honestly as possible and with deliberate inaccuracy as well. So all my calculations are only going to be right to one significant figure. I think inaccurate calculations are very helpful for constructive conversations, because inaccurate rounded numbers can be remembered and can help you keep track of comparing things with each other, which is what we need to do to figure out plans that add up. I measure energy consumption and production all in personal units. I say how much do people use and how much could we produce per person from various sources. The energy unit I've settled on for measuring energy in is the kilowatt hour, which is what your electricity meter at home probably reads, and your utility bills perhaps tell you how many kilowatt hours you're using per month or per day. I measure powers, which is how fast we use energy, in kilowatt hours per day. This makes explicit that it's a rate of using something. The physicists and the engineers in the audience will probably spit at this point and say, why don't you just use watts or kilowatts? That's a much nicer unit rather than this ugly kilowatt hours per day thing. Well, with apologies, I thought long and hard about this. A nice thing about kilowatt hours per day is, first, it is a unit that the man in the street perhaps can understand. It has the per time built in. People don't understand what a watt or a kilowatt is. And secondly, the answers come out in nice numbers that you can count on hands, or small numbers of hands. 5s, 10s, 20s are the sort of powers we end up talking about. Everyday choices come in small numbers of kilowatt hours. If you take one light bulb, a 40-watt light bulb, and you leave it on for 24 hours, then you've used 1 kilowatt hour, and it might cost you 10 cents or 15 cents. If you eat food, the chemical energy in the food you eat amounts to about 3 kilowatt hours per day. If you take one hot bath, you use 5 kilowatt hours of heat to make a hot bath. If you take a litre of petrol and set fire to it, that dissipates 10 kilowatt hours. If you have a Coke habit and you drink the Coke and throw away the aluminium can without any recycling, the embodied energy, the energy required to make the aluminium in the can, was about 2/3 of a kilowatt hour. So there's some everyday choices. And some choices use slightly larger amounts. If you drive an average vehicle 100 kilometers, then you use 80 kilowatt hours of energy. If you have a house, if you fly from London to Los Angeles and back, you use an incomprehensible number. As soon as we get into thousands, millions, billions, and trillions, we've lost people. So it's essential to avoid numbers that they all sound about the same, don't they? But they are actually different. 10,000 kilowatt hours is the round-trip energy cost, but you don't fly every day, or at least most people don't. And if we express it per day, assuming that you make one such trip per year, then the average rate of using energy is 26 kilowatt hours per day for one passenger. So again, this is in the same ballpark as driving the vehicle 100 kilometers, which you might do every day if you have a Los Angeles commuting lifestyle. If you have a house, and a typical North American house might be using 80 kilowatt hours per day. So I think this is a good size of unit for having conversations. Here's another example. In London, the mayor organized a publicity campaign to encourage people to do 7 things to make a difference and save the planet. And one of the 7 things was unplug your cell phone charger when you're not using it. If every London household did this when it's not in use, we would save 31,000 tons of CO2 and millions of pounds per year. So clearly this is very important too. It's in thousands and millions, so that's big. Well, let's personalize it. Let's just talk about one person's cell phone charger and check. It's clearly about as evil as Darth Vader, a black planet-destroying object. Here's the numbers. It's using half a watt, typical Nokia cell phone charger. So the energy saved by this conservation feat of switching it off for a whole day is exactly the same as the energy used by driving an average car for 1 second. Both of these are equal to 0.01 kilowatt hours. Now, I'm not saying don't switch it off. Do switch it off. It'll save you energy. It'll save you money. About $1 per year is the saving you'll get from this. So switch it off. But is this the number one thing we should have in a publicity campaign? Should we be distracting children's attention with these sort of ideas? Should it be in the top 7? I don't think so. I think there must be many things that come above the cell phone charger in the list of important messages to convey. So let's get some numbers into the public discussion of energy options and actually try to make a plan that adds up. Total British consumption adds up to 125 kilowatt hours per day per person. This unit, by the way, 1 kilowatt hour per day, is not just the energy used by one light bulb, it's also the average power you could get out of one human servant. So a measure of modern society in Europe is it's as if we all have 125 servants working for us. That's how much energy we're using through our gadgets and devices and so forth. The European average is 125 light bulbs per person. The American average is 250 light bulbs per person. Where's this going? Well, in Britain, the energy goes into transport, heating, mainly hot air and some hot water, and other stuff, much of it electrical. So a quick back-of-envelope conversation about where the energy goes is transport, heating, electricity. Now, when we talk about getting off fossil fuels, one of the prominent alternatives to switch to is renewable sources, and many renewables involve doing something on a land area or a sea area. And we need to talk about how much power you can get per unit area from those. The unit in which I will measure powers per unit area is going to be the SI unit, the watt per square meter. And we need to talk about population densities because people come in various population densities, and I'll measure those in people per square kilometre. 250 people per square kilometre is the population density of the UK. In terms of area per person, that corresponds to each person having 4,000 square metres. That's half of a Premiership football field there per person. So that's the huge area on which Britain's huge renewables could be harvested. Not all countries are the same, not all countries have the same energy consumption, and they don't have the same population density either. So the way these calculations are going to work out will depend on which country we're talking about. And this is a map of the world. This map shows on the horizontal axis the population density of a country, and on the vertical axis the energy consumption per person of the country. And the UK, which I was just talking about, is a fairly typical European country up in the top right here. These are other European countries in this bluish color. And America is over here with a much lower population density, nearly 10 times lower, and an energy consumption that is bigger by a factor of 2. I'm using logarithmic scales here. The vertical lines show factors of 10 increase in population density as you go across to the right, and the vertical lines are showing a factor of 10 increase in energy consumption per person. In the top left-hand corner of this diagram, we have populations with remarkably low population densities and very high energy consumptions. Iceland, Canada, Australia. Top right, the same energy consumption per person, about 300 or 400 light bulbs per person in Bahrain, but the population density is more than 100 times greater than that of Iceland, Canada, and Australia. Bottom right, Bangladesh has the same population density as Bahrain, but their energy consumption is 100 times lower, at about 3 light bulbs per person. Bottom left of this diagram, there's no one, but there used to be lots of people. Here's Africa, and they're all rushing up and to the right to come and join us in the top right-hand side of this diagram. Here's a few countries picked out, and the little blue tails behind some of these countries show 15 years of progress. And you can see everyone has increasing population density and increasing per capita consumption. Here's Sudan, Brazil, China, all going up and to the right, and the world average is going up and to the right. Now, a nice thing about a logarithmic diagram with population density and energy consumption per person is if you multiply those two numbers by each other, energy consumption per person times population density, you get the power consumption of the country per unit area. And these sloping lines here are straight lines because that's what happens with logarithms. These are straight lines showing contours of constant power per unit area. All of the countries that lie on this line here have a power consumption of 0.1 watts per square meter. So Bangladesh in 1990, Egypt, Jordan, South Africa, and Saudi Arabia all consume 0.1 watts per square meter. That's the world average. Britain over here with its higher population density and higher than world average energy consumption per capita, Britain's got a power per unit area of 1.25 watts per square meter, and the USA is halfway between those on a logarithmic scale. It's about 0.3 watts per square meter. Why is this useful? Well, renewables offer power per unit area as well, and we can put it in the same units. And now I'm going to take this diagram and squish it down a little bit into the left-hand corner and add some more green lines which show the power per unit area, roughly, of some famous renewables. Let's start by talking about wind power. Wind farms in windy places in Britain deliver about 2.5 watts per square meter. And so straight away, this diagram allows us to look at a country and say, the UK, for example, if you covered half of it with wind farms, then the average output of those wind farms would equal today's total energy consumption in Britain. When I talk about energy, I'm talking about energy in all forms, not just electricity, but transport, heating, fuels as well. So that's interesting. And if you did the same for the USA, you would have an extra factor of 3 or so. So you would only need to cover 1/6 of the USA with wind farms to match today's consumption. These rough estimates are backed up by data from real farms in Britain and by back-of-envelope calculations on roughly how much kinetic energy you can imagine getting out of wind. And so if you want to see data, it's in the book, and it's on the website associated with the book as well. So I'm always responsive to data. If I've got any of my facts wrong, let me know, and I'll update the book on the website. Next, let's talk about energy crops. Energy crops in northern climates deliver something like ½ a watt per square meter. So the message of that is, even if you cover the whole of the UK completely with energy crops, you wouldn't match today's energy consumption. America, on the other hand, if totally covered with energy crops, would just about be able to get by at today's consumption. Here's a famous energy crop called miscanthus. Here's some data on the performance of energy crops, with ½ a watt per square meter being typical. And you can get more in the tropics. There's more sunshine, the temperatures are warmer, so the enzymes work better. Next, let's give you a table with a few more renewables in it. They all come in with the same rough number of watts per square meter as wind farms. Some a little bit bigger, some a little bit smaller. Solar panels on roofs in Britain can deliver something like 20 watts per square meter. Here's data from real solar panels in Britain. And so straight away, you can work out, if you covered all south-facing roofs with solar panels in Britain, you would get about 5 light bulbs per person, as compared to our total consumption of 125 light bulbs per person. And so you realize, if you really want solar panels to make a big difference in a European location, you need to perhaps go a little bit crazy, leap off the roof and cover the countryside with solar panels, as they do in Bavaria. This is the traditional Bavarian farming method, shown by this photograph here. Once you put them on the ground and space them out, you can see the sunshine shining through the gaps between the panels, and the actual power per unit land area delivered by this solar park is only 5 watts per square meter, which is twice as good as the wind farm we started with. And the message for the UK then would be, solar parks like this, if covering 1/4 of the country, would on average match the total power consumption of Britain in all forms. And there's a very similar message for places like Massachusetts and New Jersey, whose population density is the same as the population density of Britain. Next up, let's talk about tidal pools. Tidal pools have been used for centuries, and here is one on the east coast of Britain, and here's one in France. And it delivers 2.7 watts per square meter. It's a simple back-of-envelope calculation to check that figure, using things to do with water density and gravity and heights. And 2.7 watts per square meter is just like wind farms. So we already know the answer. If you want a tidal pool to make a really big contribution, you need a tide pool not the size of a small estuary, but a tide pool the size of a country. And God, in his wisdom, when he created the British Isles, provided the British with exactly such a facility. It's called the North Sea. The North Sea is an enormous natural tide pool, in and out of which and round which great sloshes of water pour every 12 hours. And one way of getting energy is to exploit this natural countryside tide pool, put underwater windmills in the places in yellow on the map there with big currents. And here's an underwater windmill which has just been plopped into the water near Northern Ireland. No one's deployed these things on the scale of upstairs wind farms yet, but we can anticipate what the power per unit area is by simple physics calculations. Water's density is 1,000 times bigger. The speeds we can look up. And we find that underwater wind farms will deliver something like 8 watts per square meter. So that's 3 times better than the upstairs wind farms, but we still need the total of all of those underwater wind farms to be getting on for countryside. Next, Rainwater Hydro. It's a big renewable worldwide. You can work out the power available from rainfall by taking the height above sea level and the rainfall arriving at sea level and multiplying those by g, the strength of gravity. And you find for highland locations in the British Isles that the power per unit area of that arriving rainwater is about 0.24 watts per square metre, smaller than the wind farms. So the message hasn't changed. The final renewable on this list here is concentrating solar power in deserts. These beautiful mirrors here deliver something like 15 or 20 watts per square metre of land occupied by the solar power station. So that's better than wind farms, but not orders of magnitude better. So we still have the overall message. To make a difference, renewable facilities have to be country-sized. Now, we do have a constraint on us when we're making plans for the future. That at the moment we live in democracies, Britain and America, and in democracies we have to have consultation exercises. And here's a photograph of a consultation exercise in full swing in the little town of Pennacook, just south of Edinburgh. And you can see the children of Pennacook celebrating the burning of the effigy of the windmill. Because if there's one thing the British people are good at, it's saying no. And here's a few more organisations expressing their views on wind farms. So what to do about that? Well, you could say, let's go offshore to get away from the objectors. And there's a problem that the offshore wind farm proposals are also met by opposition. They ruin the scenery, they ruin the view, they're bad for airports, they're bad for surfers, and fishermen oppose offshore wind farms. Last but not least, the military couldn't possibly cope with having wind farms because it would ruin the security. They couldn't defend us from the Russians anymore if we had wind farms, ruining the radar. So, what to do? After you've had all of these consultation exercises, given the current public attitude to renewables, a country like Britain with its population density may struggle to actually match today's consumption with any mix of renewables. A rough cartoon of what you might be able to get with a big push and lots of consultation exercises is perhaps alongside this red stack which represents today's 125 light bulbs of consumption of energy in all forms, maybe you could get about 17 kilowatt hours per day per person from a mix of renewables. This is just a rough cartoon of what I can imagine we might be able to deliver in a place like Britain or Massachusetts or New Jersey. So, how can we make a plan that adds up for a region like this, and what should we think about other regions like California where population densities are a little bit lower and sunshine shines a little bit more strongly? Well, we can take action on the demand side. We could say there's no need to use 125 light bulbs per person. We can easily reduce demand. We could do that in various ways by reducing population. I'm not sure of friendly ways to do that. We could get people to change their lifestyle, but I feel a bit scared of recommending lifestyle change when I find people driving off-road vehicles, parking on the grass with cars that have teeth. And so the strategy I've gone for is to suggest, yes, lifestyle change obviously could make a difference to transport, heating, electricity, and other things, but let's leave that to one side on the table, and let's discuss the other options on this diagram. Let's talk about technology and efficiency, because we can be techno-optimists and say, oh yes, we can make things far more efficient. I'm sure you heard Amory Lovins talking in this lecture series about how we could make things 10 times more efficient easily. So let's try and have a hard look at the technology and efficiency side of things. And we could always come back to the lifestyle change if, after doing that and then looking at the other supply side options, we find we're not comfortable with the sort of plan we end up with. On the supply side, other options, if we can't transform the public attitude to renewables, include clean coal, which means that we carry on using fossil fuels, but just in a different way that puts carbon dioxide in a hole in the ground. Nuclear power, which is also a fossil fuel and has various popularity problems of its own. And thirdly, we could very politely ask other countries, we don't want to have all these renewables in our backyard, please can we have them in your backyard, because you've got such a plentifully large backyard. And for the United States, you could think of the individual states of the USA as being equivalent to the countries I'm imagining here. So New Jersey and Massachusetts could very politely ask Arizona to have solar panels in their desert so as to sort out the energy crunch that New Jersey and Massachusetts might otherwise be feeling as they try to get off fossil fuels. So let's talk about the technology and efficiency options and try and have a realistic view of what could be done there. For this discussion of efficiency options and technology switches, I'll just use a cartoon. I'll say the energy is going into transport, heating, and electricity. What can we do to make transport much more efficient? Well, here are the 5 physics principles that you want to apply. First, you want your vehicle to have small frontal area per person so as to reduce air resistance. Second, you want your vehicle to have small weight per person to reduce rolling resistance and braking losses. Third, you want to convert energy efficiently from one form to another. Standard petrol and diesel engines are only 25% efficient at turning chemical energy into oomph, and that's not very good. Fourth, go slowly to reduce air resistance and braking losses. And fifth, go steadily to reduce the braking losses. So let's apply all 5 of those principles and see what technology we end up with. We start from the standard single occupied vehicle, which uses 80 kilowatt hours to deliver 100 person kilometers of transport. And we say, apply lots of those principles, and we end up with this, a bicycle whose energy consumption is 1 kilowatt hour per 100 person kilometers. So that's 80 times as good as the car we started from. So Amy Lovins is right, technology can make a difference. But the lady in the tank on the left might say, no, 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 that's a lifestyle change. I couldn't possibly ride a bicycle. I want to zoom around in a big metal box. So here's another metal box that the lady in the tank could be offered to zoom in. This public transport, this train, uses 6 kilowatt hours per 100 person kilometers. That's 10 times as good, more than 10 times as good as the fossil fuel vehicle we started from. But the lady in the tank might say, no, 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 I can't possibly travel with all those horrible people. So she requires an individual box to zoom in. So let's apply all the technology pushes we can think of, and we end up with this little eco car. It comfortably accommodates 1 teenager. It's shorter than a traffic cone, and it is almost as good as a bicycle in its energy consumption. But to deliver this performance of just 1.3 kilowatt hours per 100 person kilometers, you have to drive it at 15 miles per hour. Maybe this isn't a satisfactory technology switch. We want something a little bit more normal, but if you have something that is about this, and you can sit in and it zooms along, it creates swirling air behind it. It will have air resistance. There's no way of getting around that. But we can attack the efficiency of conversion of energy between different forms. And petrol and diesel engines are only 25% efficient. Electric vehicles are about 85 or 90% efficient at turning chemical energy in the battery into oomph at the wheels. So here is an opportunity to have a big saving, a factor of 4 saving in energy consumption if we switch to electric vehicles. And here's some electric vehicles in Britain, and then this is a fish somewhere in California whose energy consumption is more than 10 times better than the fossil fuel vehicle we started from. 21 kilowatt hours per 100 kilometers is the consumption of this slightly strange Indian-made electric vehicle in London, and that's measured at the socket using a power meter. And you might say, but the electricity came from burning a chemical at a power station, and if that's only done with an efficiency of 35% or so, then we haven't really won anything. And that's true. If you make electricity that way, then this switch to electric vehicles doesn't give us a great win. But we don't have to make electricity by burning chemicals at power stations with an efficiency of 35%. We could get electricity from other sources, like windmills, for example. So I think electric vehicles deserve to be firmly on the table as an efficiency option, as long as we bear in mind the need for green, efficient electricity. Electric vehicles have been around for a long time. There's Edison, top left, and a world speed record holder, top right, who set the world speed record in 1899 in an electric vehicle. There's lots of electric vehicles being talked about at the moment. Hopefully they will become widespread, and some of them look like muscle cars and have energy consumptions even lower than 20 kilowatt hours per 100 kilometers. And some of them have crazy looking doors and get even lower than that. And electric scooters are perhaps the most energy efficient electric vehicles of all, using just 3 kilowatt hours per 100 kilometers. So technology can make a big difference. And a transitional technology that we could go through to get to electric vehicles might be plug-in hybrids, which have a little petrol or diesel-powered engine hidden away to recharge the electric battery if you go too far and run out of juice. And there seems to be some obligation that plug-in hybrids have to look like killer robots from the future. I'm not quite sure why, but how much energy do these use, this transitional technology? Well, the Volt claims to use 25 kilowatt hours per 100 kilometers. So that's not quite as good as the electric vehicles, but it's pretty close. And so I think it's a very good transitional technology to help us get the electric vehicle infrastructure up and running. Now, what about heating? Here, we have a very different situation in Britain, obviously, from other locations like California, where your concern isn't heating, it may be air conditioning that's guzzling lots of energy. But let me just talk you through the technology challenge for Britain anyway. Why do we need lots of heating? It's because we have crappy buildings. This is my house with the Ferrari out front. It loses heat in the winter, and the heat loss is the product of the leakiness of the building and the temperature difference between the inside and the outside. The power required to make up that heat loss is the heat loss divided by the coefficient of performance of your heat creation system. And that would be true for making hot water as well, that you make hot water by using power, and the power required is the heat that you want divided by the efficiency of some heat-making system. And we can reduce the power required for hot air and hot water by attacking the three colored terms on the right-hand side here. Reduce the temperature difference between the inside and the outside of your building in the winter. This can be done by an amazing piece of technology called the thermostat. You grasp it, you rotate it to the left, and your energy consumption will go down. If you turn down your thermostat in Britain by 1 degree Celsius in the winter, you'll reduce your energy consumption by 10%. I've turned down my thermostat by 5 degrees on average in the winter, and it reduces my energy consumption by 50%. Some people call it a lifestyle change. It works. We can also reduce the leakiness of the building. In Britain, you can do this by getting the fluff men in to put fluff in the walls and extra fluff in the roof, and maybe get a new front door to reduce the loss out of the front of the house. These sort of measures are economic, I believe, and they give you a saving in leakiness of about 25%, which is worth having. But it's not the sort of saving we'd really like if we're after a radical technology-driven transformation. To get radical change, again, we perhaps need to imitate the Germans. In Germany, a traditional thing to do with a crappy house is to coat the outside with 12 or even 20 centimeters of rock wool and put a nice finish on the outside. This really has a big effect on the insulation performance of European buildings. But there's another thing we can tackle, which is the efficiency of the heat creation system. In Britain, and I think in California, it's quite normal to get heat when you want hot water or hot air by burning natural gas. And standard natural gas burning devices are 90% efficient at turning chemical energy into heat. And that sounds quite good, 90%, but actually it's lousy because you're taking high-grade energy in the form of chemicals and you're delivering low-grade heat that has very little value. And we can do much better by being smarter about thermodynamics. There's a technology called the heat pump, which is a back-to-front refrigerator. It uses a little bit of high-grade energy in the form of electricity and moves heat from one place to another. So if you take your refrigerator and if you reach around the back of the refrigerator, you'll feel a grill at the back that is warm. What's going on? The inside of the fridge is cold and it's being made colder by some sort of pump that moves heat from the inside to that grill at the back, which is warming up the kitchen again. So you grasp the refrigerator, open the door, put it in the kitchen window with the door open. And now the inside of the fridge is in the garden and it's cooling the garden down. And the back is still in the kitchen and it's warming the kitchen up. So that's a heat pump. It's just a back-to-front air conditioner as well. And the importance of heat pumps has been recognized in Japan for over a decade now, where they've had an efficiency drive that says all heat pumps must be better than average. And the results are astonishing. You can see here Tankman and Pumpu, they've both got gloves and cape and cute eyes, the lot. They're amazing. And Pumpu's efficiency here is claimed to be 490%. Not 90% efficient, but 490%. You give him 1 kilowatt hour of electricity, he delivers 4.9 kilowatt hours of heat into Tankman and your kitchen. And maybe people exaggerate on websites, perhaps realistic performance figures are between 300% and 400% in European climates. So here's a technology we could switch to, which reduces energy consumption for heating by roughly a factor of 3 or 4. And heat pumps come in a couple of flavors. You can pump heat out of the ground, which originally came from sunshine. People sometimes call these geothermal heat pumps, but they're not geothermal at all. They're solar heat pumps taking energy that diffuses in through the ground into the house. Air source heat pumps pump the heat directly out of the air, which is what Pumpu is doing. So that's a technology option which gives us a factor of 3 or 4 saving. And the last thing I'd like to mention is another technology called reading your meters. This has had a radical effect on my energy consumption at home. I was writing a book on energy and a friend asked me, how much energy do you actually use at home? And I was embarrassed that I didn't actually know. I thought of myself as a fairly green person, but for 15 years I'd just been piling up the meter readings without looking at them. And so I started looking at my gas meter every week and my electricity meter. And the effect of just reading the meter was that my energy consumption went down from about 40 kilowatt hours per day of gas down to 13 kilowatt hours a day. These are cumulative readings for each year. This is when I started doing the weekly readings. So what happens when you read your meter is it turns anyone into a scientist. You start doing experiments. You're playing a perpetual video game. You want to beat last week's high score, and you start tinkering and seeing what makes a difference. And so I tinkered with a thermostat, and I discovered that actually leaving a thermostat at one fixed setting is not what the human body is after. Sometimes when you come in, if you've just cycled home on a frosty day, you come into a building that's at just 13 centigrade and it feels very warm, and at least for an hour or two. And that shows that if you're only going to be there for an hour or two, you didn't need to warm the building up to 20 centigrade at all. So tinkering and doing experiments, reading meters can make a vast difference. Similarly, my electricity consumption went down from 4 kilowatt hours per day to 2 kilowatt hours per day. So I halved my electricity consumption because of obsessively doing experiments. And an example of such an experiment is shown in this graph here. Before I tinkered, I was consuming a background level of about 70 watts, 1.35 light bulbs of steady consumption. And then I went round, switching off things like DVD players that were on all the time, stereos, cable modems. Switch off all of those things, and I found I had a saving of 45 watts, which is one light bulb. So that's worth doing. 1% is worth talking about. And it corresponds to a financial saving of £45 a year, which I can spend on an extra holiday in Lanzarote. And that brings us to Jevons paradox, which is when we do all these Amory Lovins things of making new, far better technologies that are far more energy efficient, we may well end up using more energy, because the man in the white van will say, oh great, I'm going to have 3 of those electric cars, they're so good, I'm going to have one for me, one for the wife, and one for the kids. So how do we get around Jevons paradox? I'm not sure. We definitely need to bear it in mind. So how do we make a plan that adds up? I've talked about some efficiency options which can reduce the demand side. On the supply side, we've got coal, nuclear power, and other people's renewables. And I'd like to show you a visualization now of what happens when we go for a diverse mix of these options: renewables, nuclear, other people's renewables. I'll show you a map of Britain visualizing the sort of thing that would add up if you go for the efficiency options and electrify transport and heating. And then I'll show you a similar map that visualizes numbers for America as well. So here's a map of Britain showing how you could supply a tripled requirement for electricity from a diverse mix of our renewables, other people's renewables, and nuclear power, and a little bit of clean coal as well. And most of this map is to scale. So, for example, the solar power in deserts is represented by these 8 blobs, which are to scale a representation of how big the concentrating solar power stations would need to be in someone else's desert in Libya or Algeria, for example, in order to deliver 16 kilowatt hours per day per person to everyone in Britain, which would correspond roughly to today's electricity consumption in Britain. And then the nuclear power this corresponds to a 4-fold increase in nuclear power in Britain over today's levels. So you could accommodate it on existing nuclear sites for the most part by having a 4-fold increase in the power stations there. The biggest renewable on the list is wind power. These squares show to scale 100 square kilometre wind farms, some of them in the sea, some in England, lots of them in Scotland, because Scotland's anti-nuclear, and that's fine in my version of democracy. If you don't want nuclear power, you get wind. And you also get storage facilities to cope with the fluctuations in the wind, and those pumped storage facilities are shown by these yellow stars here. And I'm not recommending this plan, I'm not recommending this mix. The reason I show a diverse mix with roughly equal amounts from different sources is it allows you to visualize the exchange rates and see what a plan that you like would look like. So if someone says, I don't like solar power in other people's deserts, I'm not happy with that, no problem, cross it out, and now you know that you need twice as much nuclear, so you need an 8-fold increase in nuclear power over today's levels instead of a 4-fold increase, and then you still have a plan that adds up. Or alternatively, if you say, no, I don't like nuclear power, we can cross out the nuclear contribution and go to the wind and say, okay, we need 3 times as much wind as this, so we need 3 times as many wind farms as are shown on this map, and it's just a question of where to put them. And then on average, you will still have a plan that adds up. Let's do the same visualization for America as a whole. People often say that solar is the future, solar is the answer. For Europe, people sometimes draw a square in the Sahara Desert, and they say this square is much, much smaller than Africa. It's much smaller even than the Sahara Desert, and it could supply all of the energy for something or other. Well, let me show you a square in the desert. And this yellow square here is a visualization of the area that would deliver 125 light bulbs per person. That's today's European consumption for everyone on this map, for everyone in Europe and everyone in North Africa. Obviously, that's not a plan we would recommend, but it's an interesting visualization. It's a tiny square compared with the Sahara Desert, but it is a square that's the same size as Germany. So the message is, the renewable facilities do have to be country-sized. And if you say, okay, we won't go for only solar, we'll do other things, well, fine. If they're renewables, then the area occupied by the sum of all of those things will only get bigger, because all of the other renewables came in at smaller powers per unit area than the solar facilities. So let's look at options for the USA. Here's the same yellow square in Texas. That yellow square visualizes for North America if you went for an exclusively solar approach to match today's total power consumption in all forms. 250 light bulbs per person for 500 million people would be delivered by that yellow square, which is almost as big as Texas, so that's really big. Now, what about a bit more diversity? Well, let me visualize for you some 42s. 42 kilowatt hours per day per person is what I'm about to show you. To remind you, the total consumption is currently 250 kilowatt hours per day per person, and you could approach a reduced version of that, say 120 something, by having 3 42s. So 42s are perhaps useful units to look at. Another thing that comes in 40s in America is electricity consumption alone is about 40 light bulbs per person. So each of these things that I'm going to show you is what you would need to match today's electricity consumption alone. Of course, you need more than electricity because you've got to sort out transport and industry and all those other things. So here comes some 42s. First, the wind farms. 42 kilowatt hours per day per person would be delivered by these 10 regions here, each of which is the size of New Jersey. The total of those is the area of California. So that's buildable, that's possible, but it would be a significant increase over today's levels. A 60-fold increase in wind over today's levels would on average give you something like 42 light bulbs per person. You can get the same from solar facilities in Arizona with an area about 1/8 of Arizona. And biomass, which might be useful for liquid fuels for transport and so forth, would require the area shown by these green squares here. Finally, nuclear power could deliver 42 kilowatt hours per day per person if you had a 5-fold increase in nuclear over today's levels, which I've visualized not very well by putting some purple dots on the map. So imagine a 5-fold increase. Now, this map shows the whole country, which has 300 million people, so it's a bit incomprehensible. It's not very personal. Let me show you again what these 42 light bulbs per person correspond to in more personal units. Let's actually visualize what one person or what a small community needs to do for each of those. The wind, if you want to get 42 kilowatt hours per day per person, you need to get into collaboration with 300 people and hold hands with those 300 people surrounding one of these 2 megawatt turbines. I think that's visualizable, it's doable. 300 people could put up one turbine and own it somewhere. Similarly, nuclear power, a 5-fold increase would correspond to Los Angeles having 7 nuclear power stations, Chicago having 5 nuclear power stations, and so on. Portland, Oregon requires 1 nuclear power station. So that's the community visualization of these rather large objects. Biomass, 4,000 square meters devoted to every person's biomass would deliver 42 kilowatt hours per day per person. And the solar in deserts, finally, there's a company called eSolar in Pasadena. They make these rather beautiful concentrating devices composed of rather small human-sized mirrors. You would need 30 of those mirrors per person and 1 tower between every 400 people to deliver 42 kilowatt hours per day per person from solar in deserts. So a plan that adds up from America is going to need to choose some mix of these options and some degree of action on the lifestyle side, on the technology side, and so forth. And maybe we need all of these things to remain on the table to make a plan that adds up. In conclusion, getting off fossil fuels is not going to be easy, but it is possible and it may even be fun. Thank you very much for listening. I'd be happy to take questions.
Do you have another mic in the room? in your opinion, is there any credibility to the contention that the food shortages were partially or wholly induced by cultivation of fuel crops?
Okay, the question is, did food prices and food shortages in places like Mexico, is it credible that those were caused by policies of big increases in biofuel production? Yes, I think it's very credible that exactly that is the case. The land area required for biofuels, as I indicated, is enormous. And so if the world were to try and switch to biofuels, you would, I think, almost certainly have a severe conflict with food. And even at the level of just 5 or 10% biofuels in the mix, I think we have had recent historical evidence of that conflict. So it's a sustainability issue we need to be very careful about. Yeah. Oh, okay. I think it's on now.
Hello. It went by rather fast, but did you talk about the underwater turbine options for Britain? And I was wondering about the coasts of the United States, whether the currents there might also be used.
So the question is, what about underwater windmills? Yes, so the currents around the British Isles are especially big. We have many places with currents in the ballpark of 4 meters per second or larger. And this particular device here is, I think, a 1 megawatt device. So a similar output to one wind turbine is delivered by this thing, which is a little bit smaller than a wind turbine. Does America have similar resources? Well, the famous location is the Bay of Fundy, which I think is shared with Canada, and it has very large tidal ranges and very large currents as well. There are also ocean currents all around the world, but the magnitude of those ocean currents is significantly smaller than the tidal currents on the map here. So you would need to deploy much larger numbers of these underwater windmills and perhaps make them larger to exploit ocean currents. I think the tidal currents are the ones to go for first before we start looking at the global ocean currents.
You mentioned clean coal. We hear quite a bit about clean coal in this country because, of course, it's our largest supply of fossil fuel. Are there any clean coal plants actually in operation? And what kind of energy do they require to operate? What's the loss in energy production if you start pumping the CO2 back into the ground?
Great. So what's the energy cost of running clean coal power stations, and are there actually any working? I believe there's one working in America that sends CO2 over the border into Canada to do enhanced oil recovery, which is special. And the energy cost of doing carbon capture at the power station and compressing it to a useful volume for insertion into geology is roughly 25% of the energy. So you take a 25% hit in electricity production, possibly more like 17% according to the most optimistic people in the industry. Is this being done anywhere else? Well, there's a lot of prototypes, and here's a prototype I visited in Scotland at Long Annet Power Station, which is a many gigawatt, I think a 2 gigawatt power station, a bit like visiting Mordor. And to give a sense of scale, these three things on the side are not carbon capture facilities, they're sulfur capture. So these are flue gas desulfurization devices, those three. And that has a cost of 1% of the output of the power station to run the sulfur removing. Now, here is the plant which captures experimentally 1,000th of the carbon dioxide from that power station. So, so that's the thing that needs to be scaled up 1,000-fold. And this station is participating in a question in Britain to receive a big government subsidy to go ahead and do that. So this is a visualization of capture of 1 megawatts worth of CO2, but we need to get up to the thousands of megawatts. And that's something that's scarcely been done at that scale anywhere on the planet. Here's another prototype in the 1 to 10 megawatt range. This is an oxycoal test flame that's been made out of the goodness of their heart by a company called Doosan Babcock in Scotland. So here you put pure oxygen into the place where the flame is burning the coal, and you circulate the resulting gases round and round and end up with concentrated CO2 being created as you put in the pure oxygen. So this is a sort of pre-combustion method where you pay the energy cost of making pure oxygen up front instead of the energy cost of extracting the CO2 from the flue gas. But the energy cost of doing that is very similar. The cost of extracting pure oxygen from air is similar to the energy cost of enriching the CO2. Yeah.
I have a two-part question. First, what was the Prime Minister's reaction when he received your rosy upbeat assessment? And secondly, Amory Lovins was actually here in town a month ago preaching the gospel of efficiency to Rupert Murdoch's flat earth people in private, but publicly when he was at the university, he believed that with a 30-year time horizon toward 2050, a combination of efficiency and lifestyle changes actually could get the United States within the target. And in some of your remarks, you seem to poo-poo that, and in other areas you indicate that there are huge efficiencies of scale. What's your actual assessment if you had a generational approach to trying to take his vision?
So Amory Lovins gives great talks, and he's definitely got examples where tenfold savings have occurred by being smart about technologies. I think when it comes to buildings, we could definitely have enormous savings. We could be far smarter. We have controls like thermostats that pin the temperature of a space to a particular temperature, and that's not what the humans want. Often there's no human there at all, and yet the temperature is obsessively being pinned at that temperature, either by warming or cooling, and that's terribly wasteful. Also, I understand many buildings at Caltech create their 20 centigrade air in the building while the outside air is at 20 centigrade by cooling down air with a cooling device and then warming it up again with some. So we're crazy in buildings. And in Britain, we could make far better insulated buildings so that they would need much less heating. So I think Amory Lovins is absolutely right that there are lots of opportunities. But I feel sometimes he's a bit of a technology optimist. I think when it comes to transport, if people want to zoom in a box that is roughly this big, they will create swirling air behind, and there's no getting around that. And you can make the vehicle fish-shaped, and that will help. But transport will cost energy, and I think the most realistic estimate for transport is that at the wheel, you could perhaps halve the energy required by light weighting and making the vehicle more fish-shaped. And then you could get a fourfold saving by going to electrification. So I think an eightfold saving on transport for those sort of vehicles is possible. Planes, on the other hand, I think have already been fantastically optimized. So I don't imagine Amory Lovins could transform the plane end of things. So I do think that technology can help, but I'd really caution against an over-rosy view of the potential for technology. In my rough guesses there, when I said we can make transport more efficient by electrifying it, I also assume that cheaper technology will then be used by more people. And so we'll have the rebound effect, the Jevons effect, and we have to contend with that too.
And what did Gordon Brown say when you received your first report?
Okay, I cunningly evaded your first question. What did Gordon Brown say when he read my book? I don't know, but he did sign off my appointment as the Chief Scientific Advisor to the Department of Energy and Climate Change. So I do feel very well supported by both the civil servants and the politicians in London. Who's next?
Yeah, one thing that I noticed is the 2x between Europe and the US, and I can't help but notice a couple of things that are different. I mean, one is we had a talk here recently by Jeffrey Brown on peak oil, and he said that the single fastest thing you could do is to go over to electric-powered public transit, and that affects not only the first-order effect that it's more efficient, but also it changes how people use transportation energy. But the second thing is sort of a larger issue between the U.S. and Europe, and that is that the energy and transportation is so heavily subsidized in the U.S. You pay, I believe, something like $6 or $7 a gallon in taxes in the U.K., and that's about how much that we're being subsidized in the U.S. Could you comment on that?
Okay, so where does this 2 times difference come from between America and Europe? Yes, certainly transport fuel costs far more, and the response in Europe is that people drive smaller vehicles and that they are more energy efficient. We have smaller buildings. I think the typical dwelling in Britain is half the size of an American dwelling, so all the costs associated with building dwellings are reduced. And the stuff we use is smaller. A British shopping trolley is about this wide, and an American one is this wide. So everything here is just bigger, and it still gets thrown away in the same way that people throw things away in Britain. So yeah, there's a tendency here for energy to be very cheap, and so people use a lot of it. Who's next? Who's got a microphone? Yeah.
So I'm very sympathetic to the idea of bringing numbers and sort of to make the discussion about energy more rational. And clearly in your own life, sort of looking at your power statements did that for you. I'm interested in your perspective on that and how that perspective might have changed in your role now as science advisor, sort of what your thoughts were about the possibility for rational discussions about these issues before embarking on this project and what your thinking is now.
Do I think that numbers help? Do I still believe that numbers are useful? Yes, definitely. And one of the things we're doing in the department now, there's a team working on 2050 roadmaps. We have our 2050 target already, and the question is, how are we going to get there? We're interested in visualizing and quantifying what needs to be done to get us to those targets. And I can show you a screenshot of what this work looks like. Where's it gone? I've lost my... I'm sorry, let's pick a random slide and... Okay. Here's a screenshot of the calculator we're working with, and this calculator is, to answer your question, it's having an impact, and so I think the numerate approach is a good idea. Let me talk you through how this works. We have made a physical model of the energy system in Britain, and we describe levels of effort that could be made in different sectors on the demand side and on the supply side. So degrees of lifestyle change, increased use of public transport, and levels of insulation on the demand side. And then on the supply side, we have levels of action. Do we have an Apollo program for wind power? Do we have an Apollo program for clean power or for nuclear? That would correspond to a level of effort equal to 4 on the scale. And we've engaged with experts to quantify what an Apollo program would correspond to plausibly in each sector, taking into account real build rates that could be achieved based on looking at France's expansion of nuclear power and so forth. And you can choose whatever levels of action you want on the supply side and the demand side, and then you can see various outputs, which I've illustrated here, the emissions that you would get from a particular set of choices. Do we reach the 2050 target? And this particular set of choices does reach those targets. So I'm delighted that this physics-based and choice-based approach is going down well, and it's helping people within the department understand the issues. And now the question is, how should we best engage the public in understanding these numbers too?
I have a question. Is anyone looking at ways the oceans can be utilized for either biofuel crops that can be grown and harvested from the ocean, or other things besides just tidal and wave energy?
Okay, so what about growing algae or seaweed in oceans and using them as a source of energy? Algae are plants, and so their power per unit area is going to be very similar to the power per unit area. At most, the power per unit area delivered by energy crops above ground. So the message for Britain was, even if you cover all of Britain with energy crops, you don't match today's consumption. Even our consumption of liquid fuels would be very difficult. If you took all agricultural land in Britain, you might just about be able to match today's consumption of liquid fuels for transport. So we go for algae. You need an area in the sea somewhere that is the size of Britain in order to match today's use of liquid fuels. It's an option, and there are a lot of people who are excited about algae. One way of cheating is to put the algae in a pond next to a coal power station where you get concentrated carbon dioxide, and then you can get a greatly enhanced growth rate of your algae. You need still a very large area, perhaps 10 square kilometers around one coal power station. So a large area is needed, but you get better productivity. But that is cheating because you're still using a fossil fuel. You're just getting 2 uses out of the carbon atom instead of 1. Yeah.
Yeah, so as you mentioned, in democracies like the UK and the US, there's a great deal of discussion and public debate before decisions are made as to how to do large-scale projects like this. But that's not the case in all countries. And presumably in your interaction with the government, you talk about what's happening in some other countries in terms of their development strategies with respect to energy. Do you have any insight into what, or thoughts about what direction China, for instance, might take in deploying some range of options like the ones you put out for the US and for the UK?
Okay, so what are other countries doing? What do we think of that, and what's China doing? People often point the finger at China and make them into a bogeyman. This graph just shows carbon dioxide emissions and energy consumption, and we want all countries to end up somewhere in this box here for the climate motivation. And there's no role model to point to, and it's not right to say, oh, China are the out-of-control ones. Everyone is outside the box except for Congo and Bangladesh. Here's the UK. We're committed to getting inside that box by 2050. Here's the USA, and President Obama gave a target of 80% reductions or so by 2050 before his election. So where's China? They must be somewhere hereabouts. Yes, there's China. Where's China going? Well, I imagine they're going up and to the right on this diagram, as are many countries. But should we point the finger at them? I think China, far from being the problem, are actually going to be the solution. If you ask the question, who's making more nuclear power than anyone else put together, it's China. If you ask who makes more solar hot water panels than the rest of the world put together, it's China. Who installs more of them? China. They've got 80 gigawatts of solar hot water panels on their own roofs alone, and they export a roughly equal amount to other countries. Who makes more electric vehicles than everyone else? I'm not sure, but I'd be happy to guess that it's China. So, and who's got their own fusion program? China. They've got their own fusion program comparable to the international fusion program that all the other countries are doing together. So I'm an admirer for their green activities. Yes, they're putting up lots of coal power stations, but naughty, naughty China, why are they doing that? Well, they're making stuff for us. One of the reasons why we have emissions and energy consumption that's smaller per capita than America, I suspect, is that we have less industry now in Europe, and we import stuff from other countries, notably China and India. Yeah.
Do you think that fuel cells like the Bloom box can play a large part in fulfilling our energy needs?
Okay, so the question is about hydrogen as an energy carrier. Is that another way of putting it? Fuel cells consume?
Bloom box specifically uses hydrocarbon as a fuel, correct?
Okay, so there's various sorts of fuel cells. One sort takes a fossil fuel and gets energy out. And hopefully it does that with greater efficiency than burning the fossil fuel in a standard engine, in which case I view it as an interesting, helpful technology, but perhaps not a long-term solution if we're trying to get off fossil fuels. And hydrogen is also hyped up as part of a new future, the hydrogen economy. And the question always is, where does the hydrogen come from? And it either comes from a fossil fuel or it comes from renewables via some route, or perhaps from nuclear power. And the truth about hydrogen with today's technologies is that it doesn't actually save energy. So maybe hydrogen's going to have some long-term role, but in Britain they had this CUTE project, Clean Urban Transport for Europe, and the true numbers for this hydrogen, which was powering these buses for public transport, is that the primary energy consumption to make the hydrogen was between 80% and 200% greater than the baseline bus that they're comparing with. And the greenhouse gas emissions were between 40% and 140% greater. So I feel really quite skeptical about hydrogen at the moment. This BMW hydrogen vehicle uses 254 kilowatt hours per 100 kilometers. So that's 3 times more energy input than the standard fossil fuel vehicle. So maybe the hydrogen horse is going to play a role in the long term, but I really worry that people just take a word and hype it up and they say algae, hydrogen, next generation cellulosic bioethanol, all these words, and because it's a word and people say it's exciting, people believe them, and I think we need to look really carefully at the numbers. Where's the microphone?
You reminded us that nuclear is just another fuel. As far as resources, how long would the world's supply last? Do you happen to know that? I don't know.
Okay, so the question is, how long would nuclear power last? So to answer that, you know how much uranium there is that's easily, plausibly accessible. And it's difficult to answer that question because there's not a uranium shortage at the moment. The answer to the question, how much of a particular resource is left, is often 40 years, because if there were less than 40 years left, people would explore and they would find more. And so there's no incentive to explore for more stuff, which is a costly thing to do. And that's why so many things only have 40 years left. But for uranium, there's more than 40 years left, so there's no incentive to explore. But the best estimates I've been able to dig out of the literature indicate that if you take all of the recoverable uranium, including the unconventional uranium from phosphates, then the amount you would get, well, it depends how fast you use it and who's allowed to use it. And the assumption I've made is that everyone on the planet could use it, and that it needs to last 1,000 years in order to answer your question. Then what you find is, in once-through reactors, which are the standard design in America and Britain at the moment, if everyone used it on the whole planet, it would be sustainable. It would last 1,000 years, this mined uranium, if you used half a light bulb per person. And so today's levels in America of 7 or so light bulbs per person are not sustainable by that criterion. However, we could switch to breeder reactors, and then the same amount of uranium would deliver 33 light bulbs per person for everyone on the planet for 1,000 years. So I think that's quite a realistic thing to imagine doing, though it's not the policy of many people at the moment to go for breeder reactors. And in due course, you might get uranium out of oceans, and then the amount that you could get out of oceans when put into breeder reactors is getting even bigger than 250 light bulbs. We're up to 420 light bulbs per person with ocean uranium. Nuclear power can also be driven off thorium, and the best estimates I've found of thorium resources offer something like 4 or 24 light bulbs per person. But I should emphasize, these numbers are very uncertain because there isn't a shortage, so we don't know how much uranium there really is. Yeah.
So what about government actions? In particular, I was being a government official. So in the United States, mandating higher fuel efficiency for cars or banning electric light bulbs or things like that. Should the government play a much bigger role than it is today?
Should government play a bigger role? Well, I think absolutely. For any motivation for getting off fossil fuels, I think government involvement is essential. I think that markets aren't good at solving these long-range problems, these 10-year and 50-year problems by themselves. So the markets need to be enhanced and tweaked and modified, and maybe in addition to market mechanisms such as a clear long-term price on carbon, maybe there's a need for regulation as well. People build earthquake-safe buildings in Southern California, not because there's a market pressure for that, but because of building codes. And people also buy insurance against earthquakes, not because they're sure that an earthquake is coming along, but because people want insurance and want to reduce risks. So I think government legislation that puts a price on carbon in some form is a good idea, and I think regulations on buildings and vehicles are sensible directions to be looking in as well.
What about government stimulating new invention? You seem a little pessimistic about big improvements in efficiency, but just like the invention of the steam engine, what other, why not spend more money stimulating invention? Oh, absolutely. So I have no problem at all with stimulating invention. I think it's a very good idea, and I do hope that inventions are going to come along that will change some of these numbers. However, many of the numbers I've described to you are up against the limits of the laws of physics. So the wind farms that I talked about, wind turbines are within about 10% of the Betz limit, which is the theoretical limit of how much power you could get out of a flow of air. So how can we improve on that in terms of power per unit area? Well, the only significant way to improve will be to go up, to make bigger, taller wind turbines that catch faster wind speeds. Bigger turbines then have to be spaced further apart because of the wake effects, which are visualized in this astonishing photograph here. So the power per unit area won't go up very much, but it'll go up a little bit. A doubling in height might give you a 50% increase. So I don't see wind technology transforming the power per unit area
It'll make it cheaper, and I'm all in favor of investing in wind power innovations, better gearboxes, replacements for gearboxes, and we can make renewables cheaper, and that will help a great deal. Similarly, on photovoltaics, the power per unit area delivered by photovoltaics, I'll be surprised if this goes up. Photovoltaics are terribly expensive, so I think it's a really good idea to invest in innovation in photovoltaics, because I hope the price is going to come down so that they become economic to incorporate into buildings everywhere without any subsidy. But there's a physical limit called the Shockley-Queisser limit, which applies to single-junction semiconductors. That says you can only get 31% of sunlight and turn it into electricity. That's the absolute limit. And they're already at 20%, which I think is astonishingly close to that limit. Perhaps they can do better with multiple junctions. The triple junction limit is higher up, but here's the best triple junction material I was able to find so far, which is down in the 6% efficiency ballpark. So my prediction is, yes, let's invest in technologies, and things will get better, but the thing that's going to get better is the cost of the technology. In terms of the scale of what we're talking about, I think the overall message of my talk is that the laws of physics say we're talking about a big building project, and that's not going to change. Who's next? Yeah.
Is there a possibility somebody may have looked into, or may can look into, as an additive, this rather grim prognosis, increasing the amount of photosynthetic processing of CO2 into oxygen? Is there some way to get some kind of botanical upgrade?
Okay, so the question is, can we engineer better plants and get them to photosynthesize faster? I think it's quite a tough act to follow. Evolution has been at it for millions of years, perfecting plants. They're perfecting themselves to be good at lots of things, to stand up straight in wind, but one of their big objectives in life is when the plant sprouts, it wants to be ahead of the other plants, because if it doesn't get ahead, it'll get shaded and it won't grow. So they've got a big incentive. Every single year, the plant has an incentive to grow as fast as possible. And so evolution has optimized photosynthesis amazingly. Plants are about 1/2% efficient at turning sunlight into carbohydrates that we can end up using. And I'm not sure if a genetic engineering program or plant breeding program could really transform that. When we do plant breeding to make better food, we can transform the plant and make it more productive so we get more to eat. But we're doing that by making shorter plants that have less leaves and create more fruit. So we're not actually, when we do that sort of plant breeding for food, we're not increasing the amount of energy captured. We're just switching the use of energy into a different form on the plant. So I'm a keen supporter of plant breeding. I'd say, yes, let's go for it. Let's see what can be done. But I'd be surprised if we get more, even a doubling of performance of plants. These are estimates from the literature of what could be done in tropical locations, assuming genetic modification, fertile application, and irrigation, so giving free water to the plants as well. They're predicting perhaps up to 1.5 watts per square meter. Who's got a microphone? Yeah.
I have a two-part question. The first is, you didn't talk much about natural gas, and what are your thoughts about natural gas and how it compares to coal, or clean coal? And then the second part, which is sort of big picture, which you had 4 parts to the solution, which were country-sized renewables, renewables from other people's countries, clean coal and nuclear, and efficiency, of course. I took notes. Anyways, excellent lecture. If you were to think out 20 years, what do you think the picture will look like in terms of the contribution from these 4 areas? So natural gas, and then 20 years out, what does it look like?
So what do I think of natural gas? When I wrote my book, I had the impression that peak oil was coming soon and that peak gas was coming pretty soon. Now I'm told that the game has changed, that shale gas is being extracted, and there's 1 trillion tons of shale gas that's now available to humanity. So I used to worry about energy wars over the dwindling natural gas resource. Now perhaps that worry is declining if these projections of shale gas are true, and we just have an increased concern about climate change and a decreased concern about global energy wars. What mix do I predict will happen in 20 years' time? I really don't know. It's going to depend. It's going to vary country by country for sure. So each country will need to choose some mix like this if it's serious about getting off fossil fuels. I do hope that we'll deploy not only clean coal but also clean gas, because if they're right about the amounts of gas that exist and the amounts of coal, if they're both in the trillion tons ballpark, we need to capture most of that carbon to avoid the risks of climate change. So I do hope that a large deployment of clean coal will happen, but what the relative mix of renewables and nuclear and clean coal is, I wouldn't want to predict. I just hope that we get on track to actually building something that adds up.
We could obviously go on asking questions forever, and so I think we'll bring this to a close. There is a reception now in the courtyard, and you're all welcome to join us and to ask David some more questions. But let's thank him again for absolutely marvelous work. Thank you very much.